So under this, we will look at derivation of diffusion equation. Diffusion equation. And B, Fisher-Kolmogorov. Fisher-Kolmogorov equation. Already, we have derived a diffusion equation using a random walk. Is that okay? Yeah. Now we are going to use the Fick's law. So before we start, is that okay? Yeah. Let's say the Fick's law. Fick's law. Of diffusion. The Fick's law of diffusion states that the flux, so it says that the flux equal J of the material is okay, and the flux is the amount of flow per unit area. So here, the material here can be the density of animals. It can be the density of human beings, or can be amount of chemical. The flux of the material is proportional to the gradients. The gradients of the concentration of the material. There it is. So here let's write this one mathematical. Is okay? So we can let maybe C, and here the concentration of the material. Here the concentration of the material depends on the direction as well as on the time. So the direction we can consider maybe x direction, or we can consider in 2D, that's x and y, or we can also consider in 3D, that's z, y, and x. Is that okay? So when maybe microorganisms are moving, they move what? Maybe they move up and down like this in a random manner like this. So up, down, up, down. So here we are considering distance at the same time on the time taken. So let me use one direction. So let x at t be the concentration of the material. Now, from the Fick's law, it said that the flux, that's the flow per unit area. So J is what? It's proportional. And mathematics, when you say proportional, it is a linear, so it's proportional. Is that okay? Then to the gradient of concentration of the material. If we're to be in 1D, is that okay? Like if we take what? C as if C depends on only x as a variable of x, then this is going to be ordinary derivative. Then the gradient will be what? The C or the x. But here, our C depends on more than one, and once it's more than one, then we have to use a partial derivative. Is that okay? We don't use an ordinary derivative, so we have to use a partial derivative. So that will be partial derivative. So partial C with respect to X. But here there will be normally the diffusion. It happens from a high concentration toward a low concentration. So because it's moving from a high concentration toward a low concentration, then we bring the negative. So negative tells you that it is from a high concentration toward a low concentration. Now we have to change the value sign to equal sign. So as soon as we change it, we introduce a constant. And that constant is what? The diffusion constant. So minus d del C with respect to X. Let me call it equation 1. Where d is the diffusion constant. Where d is the coefficient of diffusion or diffusibility. Is that okay? And this coefficient of diffusion, it depends on the material you are considering. Is that okay? Yeah. So now, let's say the general conservation equation or the conservation of matter in order to get our diffusion equation. So the law of conservation of matter or general conservation equation, I'm quite general conservation equation. It says that the rate of the amount of the material in a region is equal to the rate of flow across the boundary plus any material created within the boundary. So here, it said that the rate of change of the amount of material in a region or in a closed form, is okay, is equal to the rate of flow. Is okay. The rate of flow is what? Is a flux. Is okay. Yeah. Rate of flow per unit. So maybe if I have some, this is my reference point or this is my room. Is okay. And maybe water is flowing like this. Is okay. So the amount of water or the water here is okay. Per this room, that is what called the flux. Is okay. That's the flux. So here, equal to the rate of flow across the boundary. Across the boundary plus any material created within the boundary. So here, so this is what it means. if I want to know, this is my reference point, and I want to know the rate of flow here. Is that okay? It's the same as well. The rate of change of material. If I want to know the rate of change of material, then I have to get what? The rate of flow across this boundary. Then together with what? The material created what? In this boundary. Is that okay? So when I sum the two, then it gives what? The amount of what? The rate of change of what? The material. Is that okay? Because here to get it is the what? Is the outflow minus what? The inflow minus what? The outflow. Is that okay? So let's write this one mathematically. Is that okay? So assuming that no material is created within the boundary that means that the rate of amount of material in a region is equal to the rate of flow across. Is that okay? And also let's maybe x naught less or equals to x less or equals to x1. So here my x1 will be x naught plus change in x. Is that okay? Let's do that. So now let's write our equation. So once you hear the word rates, with respect to time, is that okay? And here the amount of the material is okay. That's the concentration of material. So here we are taking what? The direction as well as the time. So our C will depend on more than one. Even the direction we can consider one direction in two directions or three. Is that okay? Let's consider in one. So it means that our C here will be depend on X and T. So once we have that, then we have to use a partial derivative. So the C with respect to T. Then I can sum all the amount of the material in the region. So if this is my region, I can sum all of them. And from the Riemann idea, is that okay? He said that in order to sum it, I have to partition this one. Is that okay? And make it so small that the change of x approaching infinity, and that becomes an integral sign. So integral means sum. So I'm summing from the boundary. This is my initial x naught and x1, which is the same as x naught plus change in x. Because when I find a difference here, that is this is change in x. Is that okay? Yeah. So here I've cleaned the law. So equals to no amount is created. Is that okay? So it say what? Is equals to what? The rate of flow across the boundary. The rate of flow. So if I take my boundary, this is my x naught, and this is what? X1. Is that okay? So my x1 here, the difference is changing x. Is that okay? Which would be what? X1 minus what? X naught. You get it? So you bring this one here. So it tells you that this is x naught plus what? Changing x. Or if you add this point to the difference you get here. Is that okay? So now, is it equals what? The flow across what? The boundary. So this is where it started initial. and this is a funnel. So suppose I have maybe water flowing from here. Is that okay? Coming here. To get the amount here, it is what is coming in minus what is going out. You get it? Like maybe this is my room. So maybe water or maybe oil. It comes in and it goes out. So at any point in time, the amount of the material or fluid here would be what is coming in minus what is going out. You get it? So in minus out. So my in is the flux. So here I will get partial with respect to t x naught plus changing x c x t dx equals to, that's the flux, the flow per unit area, what is going, and that will depend on my initial point here, and then the time minus the out. This is the out. So j x naught plus change in x t, like this. Is that okay? Yeah. Now we have to integrate this. Is that okay? And here too we have to integrate this. But one of the assumptions is okay from this derivation start. We are seeing that on the summation here, so if it's independent, then this will be a constant. So once this makes such an assumption, so assuming, or since the integral is arbitrary, is that okay? Or since the integral is arbitrary, that is, it's independent of x. So this is going to be partial c x at t, or partial c with respect to t, then integral. Is that okay? Which number will be here? 1, for 1 times is the same thing. X naught to x naught plus changing x 1, then the x equals to j x naught t minus j x naught plus changing x t. So integrate 1 with respect to x. What do we get? We get x. So partial c with respect to t will be x from x naught to x naught plus changing x equals to j x naught t minus j x naught plus changing x t, like this. Let me clean here. So here we get times, so partial c with respect to t. This is going to be x naught because upper limit minus lower, x naught plus changing x minus x naught. Let's cancel, definitely cancel this. You get it? Yeah. So j x naught t minus j x naught plus changing x t. So here we get partial c with respect to t. Is that okay? Then this will be changing x. So let's divide through. And divide through, we get what? J x naught t minus j x naught plus changing x t. Is that okay? All over changing x, because I've divided through. Is that okay? This will come and multiply, so divide through. So now look at this. This looks like a partial derivative. Is that okay? Let me factor the negative out. So partial c with respect to t minus sign negative, so this will be positive. So j x naught plus change of x t minus j x naught t all over changing x, because when you expand you get the same thing. This is negative, this is positive. Is that okay? Now look at partial differentiation. How do you define partial differentiation? From our undergraduates, take loss of several variables. So partial f with respect to maybe x is defined as well. Limits as change of x approaches 0, then f of x plus change of x, maybe y minus f of xy, all over changing x. So you could see that x is changing, but y is not changing. That's why we say partial with respect to x. And the limit is okay as x approaches 0. So look here, x is changing, but t is not changing. Is that okay? So we have to take the limit as well. Change of x approaches 0, and change of x approaches 0. That means that the change is very small if you test me. So taking the limits of the limits of both sides of terms on both sides as change of x approaches 0, what do we get? We will get limits as change of x approaches 0, del c with respect to del t, then limits minus limits change of x approaches 0, then j x naught plus change in x t minus minus j x naught t all over change in x. And this is the definition of what partial derivative with respect to x is changing. So we will get, and here we don't have change of x here, so this is a limit of a constant. A limit of a constant is constant. So partial c with respect to t will be equals to what? Minus, then this is what? The j with respect to x, let's call equation 2. So in order to get our diffusion equation, we are going to substitute the Frick's law, that's equation 1. So we know that equation 1 we derive, the Frick's will say that j is equal to minus d del c with respect to x. So plugging equation 1 into equation 2, plugging equation 1 into equation 2 yields, what do we get? We will get del c with respect to t equals to, there's minus here, minus del with respect to x, and the j is this. So that is minus d del c with respect to x. And there's the second partial derivative. Is that okay? Where d is what? The coefficient of diffusion. So here, again, I get po, we get po. Is that okay? So del c with respect to t, we this constant. So d, then this is what? Del x, del c, del x. That's the second partial derivative. So del c with respect to t equals to d del square c with respect to x. And this is the diffusion equation in one dimension. So is the diffusion equation. Equation 3 is the diffusion equation in one dimension, because we have only one special variable, which is x. Now we can go ahead and derive the system reaction diffusion system. Is that okay? And then deduce what Fisher-Kolmogorov equation. And Fisher-Kolmogorov equation arises when our coefficient of diffusion is constant, and then we have only one equation, is okay, instead of having a system. So now let's move to derivation of reaction system. Now derivation of reaction diffusion system. And this diffusion equation is okay. It has analytic solution, qualitative solution, and qualitative solution and quantitative solution. Is that okay? So your assignment, this one is for elementary books. PD. Go and find an analytic solution of this. Is that okay? Analytic solution. Find a qualitative solution, and I will collect them qualitative solution and also quantitative solution. Is that okay? All the three. So now let's move to the derivation of reaction diffusion system. And the diffusion system is okay. It has a lot of applications. So diffusion is not only the amount of chemicals or microorganisms, it can be human beings. For instance, this is like Ebola, people who came from the country. That we call the diffusion. Is that okay? That's what I learned. That's the diffusion aspect. The D. Is that okay? Yeah. So it tells you that if you make it maybe SIR model SEMA, you are wrong. Because some people came. The movement, diffusion is what? Movement from high concentration to a low concentration. And the people who came from or outside their country, then we have a large number of them, and we do not have. It means that from a high concentration to a low concentration. Is that okay? So here, the reaction diffusion system. Now let's go back to the conservation. Is that okay? The law of conservation of matter. If you let law, or let me go straight. So the general, we have stated, you let it take it again. General conservation equation. Or law of conservation of matter. It states that the rate of change of the amount of material is that okay in a region. So now let's use our region to be a volume. Is that okay? It can be a volume. Is that okay? In vein or in volume. Is that okay? Vein is equal to the rate of flow. The rate of flow is what? The rate of flow across the boundary. That's the flux. Is that okay? Yeah, that's called the flux. So in non-material, is that okay? Non-material like heat or conduction. When a body is perfectly insulated, it means that you have a zero flux. It's okay. That doesn't mean zero flux. It means that no heat is gained to the surrounding or gained by the body. Because no heat is lost to the surrounding or gained by the body. It's okay. But if the flux is not zero, it tells you that heat is what? Either or being gained to the surrounding or being lost to the surrounding or gained by the body. Is that okay? So if it is losing to the surrounding, it's negative. So if you find your flux and get negative, it tells you that the heat is being lost to the surrounding. If it's positive. So here the rate of flow, the rate of flow of the material, across the surface area, let's say S into V plus the material created in V. So now let's write it. We have already written it, so let's write it again. It doesn't matter. This time we will not assume. Unlike the diffusion equation, where we assume that no material is created. Is that okay? This time we don't make such an assumption. You get it? Yeah. So here it turns out that the rate of the change of the amount of the material. So the rate means with respect to T. And here the amount of the material, that it can be the concentration or the density of the material. Is that okay? So the density or the concentration depends on the distance, the direction where the microorganisms are moving. At the same time, the time they take from one place to another. Hello, senior. With respect to T, then I can sum all the material that is changing. Is okay in the region of the volume. So by making use of this summation, that here it means that it is continuous. Is okay? Yeah. Because microorganisms, the way they move, is okay. The distance is very, very small. So here, V Cx at T is okay. The x equals to now equals to what? The rate of flow. The rate of flow of material across the surface area. Is okay? The surface area, that's along the surface area. So this is the surface area. And the rate of flow is what? Is a flux. Is okay? Then dot what? The surface element, that's the dx. Then plus what? Material created in V. So here, the material created in V. So those material, let's represent by F. Let's represent by F. So F here can depend on CXT. Is that okay? That's in one dimension. This is a spatial variable. This one is spatial variable. This one is spatial variable. Is that okay? All it depends one on one. Then divine, because it's a volume. Is that okay? Yeah. That's in 1D. And once it's from the flux here, is okay. It's from a high concentration to low concentration. We bring out a negative to indicate that. Now we have this. This is the surface or integral. Is okay? This is a surface integral, or let me use the actual integral. Is okay? Let me. Very well. Once it's a surface, it should be 2. Double integral. So j dot s then plus, this is a volume, so it should be a triple. Let me use the original. C x t given, and this is also volume, so triple integral. I've done all calculus of several variables, and all these things are applications of calculus of several variables. So partial with respect to t, triple, like this. And looking at this is a surface integral, but we can convert the surface integral to the volume. By which theorem? Is that okay? By which theorem can you convert it? Or which theorem gives us a relationship between the surface integral and the volume? It's a divergence theorem. Is that okay? So divergence theorem, you have forgotten. Divergence theorem. So most of you are doing 2 and 4. You thought what you are just doing for fun. Divergence theorem. So it gives us the relationship between the surface integral and the volume. And what the divergence theorem means is that the volume is okay. The volume is the same as surface. So for instance, if you take the heat, if you want to know that your car engine is what, you put your hand inside the car engine, you put it on top. So whatever the heat you get on top is the same as what is inside, and that we call the divergence theorem in mathematics. Or if you go to the hospital and you ask a nurse to take your body temperature, you will not cut your skin and put the thermometer inside. You put it outside, and that's what the divergence theorem says. What is outside, or the heat outside, is supposed to be inside. Is that okay? That's the surface integral become a double integral become a triple integral. Is that okay? So let's say the divergence theorem. So divergence theorem. So here, theorem. Divergence. And this divergence theorem is just extension of the Green's theorem. And the Green's theorem, it gives us a way to convert line integral, that's single integral to double. Line integral to a double integral. Is that okay? Or double integral to a line integral. So here, divergence, suppose, or you can also call it Gauss law, Gauss theorem. Gauss was brought by a German man called Gauss. Suppose that Q is contained in R3. This R3 is bounded by the closed surface, the Q, and Nx, Y, Z is a normal vector. A normal vector is a vector which is perpendicular to the plane. For instance, my hand is perpendicular to this surface. So this is the plane. So that is a normal vector. N denotes the exterior unit normal vector. To the surface, the Q. Then if the component of f, x, y, z have continuous first partial derivatives, first partial. These things are elementary. continuous first partial derivative. Now, when you find our first partial derivatives, it is continuous. Is that okay? And no continuity. Is that okay? The limit of the function should equal to the limit equals to the image. So now, partial derivatives. In Q, we have f dot and s. The Q, that is the surface, equals to the triple integral, the volume. Is that okay? Nabla dot f divin. This is the divergence theorem. Is that okay? And what is this? This operator. This is called divergence operator. Divergence operator. Nabla dot. And Nabla cross is what? Is a curl. Is that okay? And with that, there's a Nabla like that. Is that okay? Maybe times the function will be a gradient or a grad operator. Is that okay? And this since we have done it on a grad calculus for several hours. Is that okay? And you know this one, this Nabla or glad. Nabla is what? Partial with respect to xi plus partial with respect to yg plus or partial with respect to zk. This is a Nabla called a Nabla or glad or the grad operator. Grad. Is that okay? So here, this is the surface. Is that okay? So what it tells us that the surface here becomes the volume. So in order to get this term, always you take the function here f. Is that okay? So at the end, when you have the surface side, then it will be dive. Is that okay? Or Nabla dot of this. Then you change this one to vin. So now let's apply it to our equation. The general conservation equation we wrote. So if I call here 2, so let's record the 1. Record equation 1. Equation 1 was what? That with respect to t, triple integral v of cx maybe t dx equals to minus the surface integral of j, the flux dot the surface element plus the material created, that's f, maybe times cxt divin. We are going to apply it to this side. Is that okay? So look at this. That's the side. Is that okay? So all what we are going to do is what? We change the double to a triple. And then this operator dive. This will be dive 1. Dive G. Is that okay? That will be dive G. So here we will get putting or substituting 1 into 2. Substituting equation 2 into, or applying the divergence theorem. Applying the divergence theorem. Applying the divergence theorem to the first term on the right hand side. On the right hand side. So we get our triple integral we get del with respect to t triple integral v cx t dx equals to minus, and become a triple integral v, then div, this is a div g, then div g plus f pen of cx t v, like this. So now you see these integrals, it will just go away. Not that integral cancels integral. So the integral is arbitrary, or we can push all of them to left hand side. Let's do that. Let's push all of them. You can push all of them. So here, our partial with respect to t is okay. Triple integral v cx t dv plus triple integral v div g dv minus triple integral v, then f depend on cx t dv. Is that okay? And since integral is a linear operator, this is where your math have to come in. Function analysis, linear operator. Is that okay? Linearity. Mapping say that x goes to y is a linear operator if what? I take alpha maybe x plus beta maybe x and y. Is that okay? These are scalars equals alpha t of x then beta or t of y. So the x and y are always coming from the domain. Is that okay? X and y coming from the domain, and alpha and beta are scalars. What this means is that you can separate. That's what it means. So this t here can be an integral, it can be a differential, it can be a matrix. Is that okay? So it tells us that when you have something you can separate. So if you have this, you can combine, join like this. So if my t is what? It's a triple integral operator, then I can join fuse them, because integral is a linear operator. So by the linearity of integral, by the linearity of integral operator, is that okay? So here I have del with respect to t triple integral v, then cx t, all the v, you get it? Plus div g minus f cx t, all the v equal to 0. And look at this. We are integrating. This is my integral. Or since the integral is arbitrary, then what is here? Integral should be equal to 0. Or I'm integrating this to get 0. Can I integrate a function and get 0? Maybe x? No. Okay, x, I'll get x squared over 2. If I integrate maybe a constant, maybe normal, maybe 2, the x, I'll get maybe 2x. But the only way I can get that is if I integrate 0, I'll get a constant. Because I differentiate 0, I get a differential constant, I get 0. So when I reverse 0, I should get a constant. So this tells us that when you integrate 0, we get what? Constant. And look at the constant here. This constant is 0. So it means that this integrand here, for this equation to be satisfied, this integrand here must be equal to 0. Is that okay? So here, so this implies that, oh, the double integral should have been here. It should be outside this. So this should be partial with respect to t. Is that okay? Partial c. So triple integral should come rather outside. So this implies that partial c with respect to t, x at t plus div j minus f c x t must be equal to 0. So if you send this one there, we get what? Partial c with respect to t. This is in one dimension. X plus dot j should be equal to f of c x t. And this is the general conservation equation. So now let's substitute the flex law. Is that okay? Let's substitute the flex law and see what we get. Or even let me send this one also there. Let me send it there. Substitute the flex law. When I even send this one there, I'll get partial c with respect to t equals what? F of c x t minus div j. Let me write that quadrature form. So this is the general conservation equation. But we know the j, that's the flux, which is given by the Fick's law. It's okay, by Fick's law, applying the Fick's law, that is j is equals to what? Minus d del c with respect to what? X. You get it? Yeah. If you do that, what do we get? Our del c depend on x and t, or x, y, z, t. In general, t equals to f c x t minus div. This is divergence. Now j is what? Minus d del c del x. And this diffusion coefficient is not always constant. Is that okay? In some cases it is not. It will be a variable. That's when, if the organisms are interacting, then it is not a constant. So again we fall. So our del c with respect to t equals to f of c x t plus div of what? D del c del x. That is del c del x. Yeah, that affects. So here, this is diffusion equation in one dimension. So let's consider in 3 dimensions. Is that okay? Let's consider in 3 dimensions. So if I take in 3 dimensions, so in 1 dimension, then my nabla will go down with respect to xi. You get it? Yeah. So consider in 3 dimensions, assuming C is in 3 dimensions, that's 3D. That means we are looking for the horizontal, vertical, and also as well as the depth. Is that okay? In 3D. Then the Fick's law here. It tells us that our J will be minus D del X del C with respect to Xi plus del C with respect to YJ plus what? Del C with respect to 0 K. In other words, this is the same as minus D operator C, something like this. And my nabla, my nabla is what? Where nabla? This is nabla. It's okay. It's del Xi plus del YJ plus del 0 K. So this would turn into a nabla C. Is that okay? So equation 5 becomes so this will go del C with respect to T equals to F C X T in 3 dimensions, sorry. C X Y Z T plus div D, then partial C with respect to X. This time this is a nabla. Is that okay? Become a nabla C. So that is nabla or glad nabla C, like this. Generally, is okay. D is not constant, and this is what we call the reaction diffusion system. The reaction diffusion system. Is that okay? So equation 6 is called the reaction diffusion system. So this is any arbitrary function. So once it's a system, then is what we have multiples of it. So I can even make here I. Is that okay? And this is also I. Maybe Ci. Is that okay? Like this. We call the reaction diffusion system. So now look at this. This one is a vector. Is that okay? This is a vector. Nabla this is a vector. So this vector dot this is okay. Leads to a tensor calculus. So this side we need to tensor calculus. Some of us did not take undergraduate courses here. Final year we teach tensor calculus. Is that okay? Yeah. So if D is not constant, then this side comes from a tensor calculus. So we have to, maybe if we have an application, then you have to apply all the tensor calculus. Is that okay? Yeah. So we can even write this one, sum. Is that okay? You can even write sum. So it tells you that the DI is a square matrix. It's a diagonal. So DI, where DI is diagonal matrix of divisibilities. So what this means is that you can have a partial C1 with respect to T equals maybe any function. Maybe it can be xy. Is that okay? Maybe xy plus maybe number. If I take it in 1D or in 3D, that will be partial xi plus partial with respect to yj plus partial with respect to zk, or dot, something like this. Then we have a matrix, a diagonal matrix, or let me call it D1, then we have C1, something like this. Then the second equation, I have the C2, the T, maybe equals maybe x plus y squared, that's the function, plus do all this, del xi plus del yg plus del zk dot d2 c2, a system of equations with a diffusion aspect. That's what this one, the expanded form of this one, compressed in a compressed form. So when G is a constant, when D is a constant, you know differentiation, differential operator. Is okay? When D is a constant, then what? Differential operator is what? It's a linear mapping, or it's a linear operator. Is okay? When you say a map or mapping, the other name is what? Operator or a function. That's the name. Is okay? So function is the same as mapping. It's a mapping function. That's it. So here, if D is constant, if D is constant, then equation 6 becomes, and why is a constant? Because of the linearity, then we bring this one outside. Then partial C with respect to T will be F, or you can just simply write F plus D, then this will go into it. Is that okay? Dive nabla or glass C, like this. Is that okay? If this is a constant, then you can push it outside, but if it's not constant, you can't push it outside. So here, what do we get? Or if you want to bring x, y, you can bring it. If I want to bring terms C, X, T plus D, X, Y, Z, or let's make it simple F to make it so easy. D, then dive, nabla C. Is that okay? And then dive, nabla C is equals what? because what? That will give us Laplacian of C. Is that okay? That you did it, calculus of several, that will give Laplacian. If we dot what? Nabla dot what? Dot nabla. You get what? Laplacian. You get Laplacian or Laplacian operator. You get it? Yeah. And this Laplacian, for this one, Laplacian operator. Laplacian operator. And Laplacian operator is what? Del squared that. So that is Laplacian. Laplacian is del squared with respect to a squared plus del squared with respect to y squared plus del squared with respect to z squared. We call it Laplacian operator. And we can see this in Laplace equation, Poisson equation, heat equation, wave equation, Black-Stokes equation, fluid dynamics. Is that okay? Transport equation. So we get a Laplace equation, and we can prove this one like this. We can prove it. Is that okay? Can show that this is equal to this. That is the nabla dot nabla. This is defined as del with respect to xi plus del with respect to yj plus del with respect to zk dots del with respect to xi plus del with respect to yj plus del with respect to z k. But we know that I dot I is 1, j dot j is 1, k dot j is 1, and I dot j is 0. Is that okay? If you dot different unit vectors, you get 0. So here we dot the same thing. So this dot this. So del the x, then what? Del the x. And this is what? Del squared x squared. So this will give us del squared del x squared plus this dot this is what? Del squared del y squared plus del square of del z squared. And this is written as this. It's not a triangle, and that we call Laplacian. Laplacian operator. Laplacian. So it tells us that when d is constant, then we get a Laplacian. That's the second partial derivative. And the assignment I gave it to you, which is what? The invasion, the special spread of what? Predator prey. Is that okay? It's an application of this when d is constant. Is that okay? That's why you have a Laplacian at the tail end in 1D. That's a Laplacian. So yeah, C equals to F plus D Laplacian of C. Like this. So this is a special case of reaction diffusion equation. So this is a reaction diffusion equation where Laplacian is del squared del x squared plus del squared del y squared plus del squared del z squared. That's Laplacian operator. Yeah. So equation 7 is a reaction diffusion equation. Reaction diffusion equation for constant coefficient of diffusion. Constant coefficient of diffusion, D. Now let's derive what? Fischer-Kommer graph. Fischer-Kommer graph is a special case. When you substitute the f of what? Of logistic function. Is that okay? Or logistic model. When you substitute that f here and consider in one dimension, then we call it what? Fischer-Kommer graph equation. So Fisher-Kolmogorov equation is what? Is a modification of what? Of Verhoeven's what? 1832 what? Model. Is that okay? So when you substitute the logistic F here, then it comes the Fisher-Kolmogorov. In other words, Fisher-Kolmogorov equation is when you add what? The diffusion part to a logistic equation, which is a special case of what? The reaction diffusion. So now Fisher-Kolmogorov equation. Now in equation 7, assume you substituting the logistic function you let me write it somewhere here. Logistic function by Verhoeven 1838. Is that okay? That is, we know that a logistic model is what? The P or the T equals RP 1 minus P over K. So this is what? This is a logistic function, F of what? P. And that is the F here. Have you seen it? So the F here can be anything. It can be even the competition function. For competition model or competition model, you have the X, the T equals to something here, the Y, the T equals to something here. If you replace it by here, is that okay? Then it becomes what? Reaction diffusion. Is that okay? That's the application. So where this in general is a system, a vector. It means that it can be 1, 2, 3 up to certain. So this is a generalization. So reaction diffusion, that's all for that function. That is F of P equals what? RP 1 minus P over K. You understand what this is? Where K is the carrying capacity, R is the intrinsic growth rate, and the rest. Is okay. And moving and the population species moving in X direction. So our nabla there, our Laplacian will be what? Just 1D. So this means that our is a function of what? P. So C will change to P. So partial P with respect to T equals to our F is this. R times P 1 minus P over K, then plus D. Is okay because it's in 1D. Is when you know this Laplacian is what? Del square X squared plus what? Del square Y squared plus what? Del square or Z squared. In 1D means this is out. So X squared or our C change to P, equation 8, and this will call Fisher-Kolmogorov equation. So this is the diffusion aspect. Is that okay? So it tells you that if a disease and people are moving to a particular geographical area, is that okay? This is the movement, that's the diffusion. That's the diffusion aspect for the diffusion. So here, equation 8 is called the Fisher-Kolmogorov Fisher-Kolmogorov equation in one dimension. In one dimension. Because only one spatial variable, x. T is not a spatial variable. Spatial variables are x and y and z. Okay. So let's end the first lecture. My technicians are going to set up the machine again for a second lecture. So do not go away. Is that okay? Goodbye. Boss, you can pause it. So now let's continue. So I'm giving this assignment. Go and look for analytic solution, qualitative solution, that's a stability. Look for analytic solution, qualitative solution, and quantitative. Is that okay? Quantitative is a numerical approach. Yeah. And you could see that the diffusion equation we derive, if you cover this one, that's the diffusion in one dimension. Have you seen it? If you cover this, that's a logistic equation. If you add the two, Fisher-Kolmogorov. You get it? So undergrad we did this. Partial or maybe u with respect to t equals what? D partial. This is the second idea. Partial u with respect to x squared. This is the diffusion. And this one, the solution in books, is okay. So this inhomogeneous, in other words, inhomogeneous diffusion equation. This is the inhomogeneous part. So if this is change here P, this is P, is that okay? So this is a homogeneous. It's a homogeneous or PD, partial differential equation, which you learn undergraduate. So this is what? Inhomogeneous. PD. Is that okay? Partial differential equation. So the assignment is that 1. Find the analytic solution of Fisher-Kolmogorov equation. And 2. Determine the stability or discuss the steady state solution. Discuss the steady state. Steady state is the same as a fixed point, again, steady state solution of the Fisher-Kolmogorov equation. And third one is what? Quantitative. Perform quantitative analysis. Quantitative analysis of the Fisher-Kolmogorov equation. Now let's move to one of the applications of our Russian diffusion system. That is the spread of predator-prey. Is okay. The spatial spread of predator-prey. last time the note I brought it. I want it. I need information. So application of reaction diffusion equation. When the last time my laptop. If you do you know the file number of questions, do you know where it is? The one that is yes, extra file number with desktop in a KNST. If you click KNST, go to questions. Then you see Math 514 a PDF. Unit from 1. Question. Yes. Okay. KNST file on the desktop. If you open that, you see questions. You open that file. Then 6 from Math 514. So now, application. One application is spatial spread of predator or the spread of prey species. The model I gave it to you was, for example, go and do it of which you couldn't do. You couldn't even non-dimensionalize. So here, we know predator prey. What a predator prey model. When you say spatial spreader, it's in a diffusion movement where people move from one locality to another, maybe from Kumasi to Tamale. That's what we say diffusion. Is that okay? Yes. That's the movement where people move from one place to another. They are diffusion aspects. And once they are moving, it's okay. Anytime they spread they will move from a place where we have high number there and move to a place where we don't have anybody there or a low number there. It's okay. And we define diffusion as well, from a high concentration to a low concentration. So they are moving to a low concentration. That's called spatial spread. So here, predator prey model. Predator prey. But before then, let me write the reaction diffusion. Del C with respect to T. So this I, F, is okay, plus dive D nabla C. And predator prey model is okay. If we assume the diffusion is constant, then these are people who are coming in. Is okay. They are coming in with a constant diffusion. Then this becomes once a constant, this becomes del C, del T I, F I, where I plus D Laplacian of Ci di for all I move from 1 to up to maybe n. You get it? This is a reaction diffusion. So what the predator prey model, the X or the T is what? Here X for the prey, X at and Y for predator. This is a prey population. And this is what? Predator. So first you consider a hypothetical situation. This is what I'm looking for. When there are no more predators, the prey will go on unboundedly. That's the assumption made by Logical-Volterra, the observation made by Logical-Volterra. So they will go abundantly. Alpha, maybe the model you consider, the prey population grows for logistically. So Rp1 minus P over K. Is that okay? That's the F1. In the absence of that, then dy dt. But this one, it was assuming it grows or it dies or exponentially. So certain constant, maybe minus maybe alpha. Oh, this is x. So here should be x. But because we have a partial square with respect to x, let me change this x to maybe u and v. Let me use uppercase u. Thank you. And let me change here to the big V. So this would be alpha of v. Then plus. Then consider a situation when the two of them come together. When they come together, what will happen? The prey will consume. The predator will consume the prey. Like sharks and what? And herrings. Is that okay? Or sharks and fish, they will eat. So when they come to that interaction, it will cause what? This population to decline. Is that okay? As a result of this one eating what? The prey. Is that okay? And this one will grow. So it tells you that this is what? To be negative. Is that okay? For this population. Negative what? Denotes what? Decrease. So interaction. This is u and this is v. So u v. That's the rate at which they eat them. Let's use any symbol. Maybe with symbol. Maybe b. And the rate at which this one is eaten is not proportional to the rate at which this one grows. So u v. Then let me use maybe any symbol, kappa, maybe, no, or here, let's use beta. And here, this side, or kappa. And it's gamma. Gamma. Now, this is a predator-prey model. It's okay. But here, the paper is okay. That paper is okay. That discusses this. You realize that the predators, for instance, when you take a lion and maybe zebra, is okay. They move from one country to another to chase for them. That's the social spread. Is okay. So once they move, so now this is the F, and this is the CI. Is okay. Once they move from one country or one geographical area to another, then we have to deal with the diffusion aspect. Is okay. So this is going to be first one, D1. Then we are concerned in one dimension. So in one dimension, this means that for predator-prey model, I is 1, 2. We have answered 2 equations. So our Laplacian will be del squared, the x squared, because we are concerned in one dimension. So del squared, the x squared. big F squared. Over Ci, what is your U of U? Then plus, is it okay? This one to a diffusion, is it okay? The way at which it diffuse is different from this one. So they're called D2, big D2, is it okay? Then the Laplacian, the squared, the A squared over Ci, and this one C2. So this one is what? V. So 1 and 2, and that is the model. So this is this one, this is the general form. So where Fi is this, the Fi is this, the Di is D1, D2, and then Ci is this one, and then the Ci dt is this. Yeah. So that's why I say application. Then is example of it. So now we have this. We can non-dimensionalize. So now non-dimensionalize. Equations. There is no systematic way of non-dimensionalized system of equations. Different people can come up with a different equations to non-dimensionalized system of equations, but the most important thing is we have to do the normal parameters. That's the essence of non-dimensionalization. Is that okay? And also change it to a proportion. Do you get it? So that our solution will be bounded or will be invariant. That means that the solution will stay in a closed form. So our total population will be 1. Because the population keeps on increasing. If I know that my total population N in Ghana is 30,000 million, then I divide N by N. That's 30,000 million by 30,000. I get 1. So always I know that my total population is 1. And the other ones will be a fraction, upper fractions. Not necessarily go and count people, you know the number of people. Once you non-dimensional, everything is 1, total is 1. So to non-dimensionalize, we start with what? With the derivatives. That's the trick. And there's no systematic way and there's no rules for non-dimensionalized one. All what you have to be creativity. So we start with the derivative. So I can define small u. I want to change the big U. I can redefine small u. But normally when we have a fraction, let's say fraction with carrying capacity, is that okay? You want to avoid that. So when you have fraction, then you have to redefine it. Is that okay? So I can say small u equals to big U over K, the carrying capacity. Then the V, so small v, is that okay? Should be equal to what? Big V, I can multiply by any of the parameters or divide. But the trick is that you can always start with 1. Do for the first one. And then time. Normally we change the time to tau. So then you change it to tau. But if I want to, this one will make here u. So it means that this parameter will go. You get it? Here, R, we know R, K, beta, D1, D2, alpha, and gamma. They are parameters 1, 2, 3, 4, 5, 6, 7. So you want to reduce them. And the essence of reducing is to make analysis for easier. Okay. So if I can remove this R2. Is that okay? By way of saying that multiply here by R, so that if T is what, if I find T will be tau over R. Tau over R and will cancel. T will be tau over, so tau over R. When I different 1 over R. No, then I have to divide so that it will multiply. I'll get R tau because R is here, so that here will be R. Here to do the R here and cancel. If I make it like when I differentiate, I get 1 over R, but this is what R. So I'd rather divide. And that is what you now be doing. Trying to have to be creative. Check where it cancels. Creativity. And don't want to be creative. So now, then I have to also change this one. The partial, second partial derivative. So I've already defined u. Is that okay? So I can define big X in terms of small x. So big X equals to small x. Then let me multiply by something. Here, for the second partial derivative, this big U del x squared is the same as del with respect to x del U with respect to x. This is not this the squared U as we did in the assignment, as if you don't understand the derivative. This is not d squared times U over d times x squared. No, it's wrong. That's what we did in the assignment. Or a change. Second change is U over this. It's not this times this. It's not that if I multiply del squared times U, I'll get what? Del squared U. Then if I also divide what? Divide del times what? X squared. Then I'll get what? Del x squared. That's what we did. It's not an algebraic expression. Or you can leave that as we are doing. We will see what to do. This and a thing. So here, all what we have to do is we change the derivative. So I write the big U del T. Is that okay? And from all, make use of the change rule. Look here. I want, if you have y equals to maybe 3x squared plus 2 raised upon 6, find all dy dx. What do? You let u equals what? 3x squared plus 2. Why? You want to reduce the complexity. That is why you do that. So my y equals what? U raised upon 6. Then now my dy dx is what? You repeat the numerator, dy. Then the new variable you have introduced what? Du. Multiply by the same du. Then repeat the denominator dx. Multiply, this cancels. And this is called a change rule. Change rule. So the same thing here. For the one, the same thing. Is that okay? That means that, look here. Now my y depends on what? Depends on the u. Is that okay? So I can find a change in y with respect to u. Not that I can multiply or d by y and get dy, and also multiply what? D times u and get what? Du and divide it through. No. My y depends on u, so I can find change in y with respect. That's what we write this. Change in y with respect to, I can find what? For now, y depends on u. Y is no more depend on x. And then also u is depend on x. Is that okay? So I can find change in u with respect to what? Change in x. It's a change. So here I'll repeat my du over. Now my u depends on what? On small u. Have you seen it? Big U equals what? K small u. Depends. So I can find what? Change of what? Big U. This time with respect to small u. I can multiply this by this. I can multiply this times small u, then this times tau, and get du the tau. No. Because because u depends on small u. So I can find change in big U with respect to small u. Change. Big U du times multiplied by the same thing du. Now looking here, another new variable we have introduced is tau. Is that okay? In other words, the denominator here t time. Now t depends on what? On tau. So we can find what? Change in tau with respect to what? T. The new variable is what? The tau times the tau over what? This cancel. Is that okay? This cancel. Then what? Repeat the denominator like this. So my aim is once I have this, I've written my non-dimensional equation. It means that I have to change the big U to what? This is now U to small u, then big T to what? The tau. My aim is to change this to this. So it means that I want to tag this one. So we define your aim. So I will find the big U, the small u, which is what? This, the kappa. Then the tau, the T, the tau, the T. Well, 1 over r. You get it? Yeah. 1 over r. So then if I multiply, I get k over r. Oh, then I have to multiply. Otherwise, it will not cancel this r. Out. So when I put these two here, the u, the t will be the result. Kappa r, then the u, the tau. If I call here 3, now the whole of this will be your kappa times r. Is that okay? I can clean this one for free. Kappa r du the tau. Once I have that, then here when you make this one, so you get kr. So here, look here, u is now ku. Yes. So u vin. That's how you get a non-dimensional equation. You think those who write paper, they have what? Supernatural brains, or those who do it in their work. Once they have supernatural brains, they are like you. Ku vin, like this. But here, we are going to have rk small u, 1 minus small u, and here too, have you seen rk into common term? It means that here too, there's k here, there should be r. There should be r multiplying by this, so that it will cancel throughout. And then if also I want to remove the beta, it means that this one should be changed to what? R vin. Then if I also want to cancel the beta here over beta, something like this. So it means that my vin, big vin, should be called R vin over beta. But we don't write this as non-dam, so that people will suffer. So vin, small vin is what? Beta, big vin over R. So small vin equals to beta, big vin over R, like this. So that will cancel. So once I have that, then this place, beta u vin, give me what? Give me beta u is what? K small u times big vin is what? R vin over beta. So that this will cancel this, and I have my own K out. So now this one is solved. I will come to second partial derivative to get a change here. So del squared big S squared u plus del x del u instead of x bod mass bracket first. So I'll search for del u with respect of big X. So I'll repeat my del u, and del u depends on small u. Are you seeing it? So it means I have to write my change with respect to small u times the same term, small u, so mathematically, so that it will cancel. Then this big S defined in terms of what? Small x. It's defined in terms of small x. So it means that it should be what? Another new variable is small x. So small x times the same term, so that mathematically it will cancel. Then we push, look at this, put it here, big X, like this. Now when I do it like this, no term, look at the common term that is coming out. RK. It means I must put something here that will bring what? That RK out. So I can say even if I want to cancel D1, I'll divide by D. So RK is a common term. RK. If I want to cancel this D out, then I will divide here by D1. If I want to cancel the D2, then I will divide here by D2. Then we cancel the D2. So I divide here by D2. And because it's a second, it's okay. If I make it like this, when I differentiate 2, I'll get this one squared. Because I'll make this one half. I'll half it because half plus half will give me 1. That's why you see most of the models where they have what non-dimensional second partial, you see this half. So the half plus half will give you 1. Okay. So this will be my for the x d2. I bought a consumer the du dx partial u small u with respect to x small x with respect to big X. So my aim is to change what? The big U, the X to what? The small U, the small X. That's this one. So I won't tamper with this one. You get it? Yeah. So if I differentiate well, this one, the big U with respect to X. This is what is giving me K. This will give me K. So making this one, this is obvious one. Then X with respect to big X. If you differentiate this with respect to this, this is 1. There one. Then X respect to big X. So this is what? 1 times this. Yeah. This is obvious. RK over D2 is the power R. The U, the X. That is important. You can do it. That's what is in the bracket. Then I also come and get this one. So if I look at what is here, or you can just look at the U here. So now this is that. So that with respect to big X. This is that. Now big X depends on small X. That it should be, as we introduced, new value small X can be the same thing. Small X over this time of big X. You get it? Yeah. And my aim is to change what? That with respect to big X to that with respect to small X. So I'll find this one, which will give me what? K times that. Which will give me RK over 2 half. So I have indices will be 1. So for simplicity, you can just write this one. The square U, the X squared, as you combine on them. The small X times what? The X with respect to big X. Then what? Do all this. Then U dot the U, the X times the X, the big X. Right? Pew, finish. Together. Yeah. You don't want that way. Then this one becomes, and differentiate, you get what? RK over D2, or raise the power half, that with respect to small x. So if this is 4, there's 5, there's 6, then you put 5 and 6 here, you get your shakabu. I don't want to clean this. I don't want to clean it. And this one is practice, it's not perfect. And me, nobody taught me. It's not in any book, it's not in any paper. I sit down, went through it several times, sit down, do it, you get it wrong, do it. Then go and write, you change your calculus. And do it, I had one. And look at how you had the first one. You take another one, you do it. Like that, try to keep it perfect. That's what you, as a postgraduate, you should do. So always be sit down and do it. Think. And you don't want to think. You don't want to revise. Then take the whole calculus, be reading, doing it, as if you are going crazy. That's what you should do. So they are squared U with respect to x squared, because what? This is what? R K over d squared or half that which is equal to x, small x. Then this is k what? K bracket r k d squared half del u del x. It's a color. Yeah, pion. Have you seen it? This and this. Be one. That's why I put this half here. Times is 3, put 3 there. I did it times and saw the trend. So k, then rk over d squared left with 1 del small x del u del small x, and this is the second partial derivative. This is what we call the second partial derivative. So here you get what? K rk over d2 del squared u with respect to x squared. So del squared u over x squared. So this side becomes this. So now let's put all of them there. Putting all of them there, what do you get? You get du dt is what? Now you can label them since put all of them. So plug in equations 3 to maybe 6 into 1 notes. This side is now kr du d tau equals to this r. Is okay. So express u, big U, you get what? R k small u, then 1 minus this over this is small u. You have rather seen the paper. Oh, I've even conjure one. You hold it. Conjure one. Yes, non-damage. Different people can use different approach. So minus. Is okay. Beta. Then the u is what? Is k small u. Then v is what? R small v over beta. Then plus d1. Then the whole of this is this. That's k rk over d2 the square u the x squared like this. So that this will run through. This will cancel this one. And this rk will run through. That's the essence of doing that. Make sure that it will run through. So you get what? Du d tau, which is what? U1 minus u. Then you get minus uv plus k d1 over d2 the square u s square. And when in non-dimensional, there shouldn't be what? the new variable. There shouldn't be any new variable. Is that okay? Yeah. You should be able to get rid of them. So even the k, I could have gotten oh, this one's half. Is that okay? Half times half is 1. So if R was here, I push R here. My k. So that I've got what? So that I want to maybe represent d by d1 over d2. So that I've got rid of them. So what I can do is my del squared x squared equals what? Del the x del u dx. I express this as del u with respect to small u times small u small x with respect to big X. So this one gave me the k, and this one gave me half k. It doesn't matter. We can redefine this. We can redefine this. Or this is the k. Oh, I can get rid of it. K. So the other one too get the same half. So r over d squared all over 4 half. Then I won't bring the k here because I want this k to go. Because this will produce a k. Is that okay? So that's what you should be doing, non-dimensional. You do it, you come and clean, you correct it. Is that okay? So you get simple equation. What you get. So that this here will be k del u del x times what? This will be r over d2 half k. And then my non-dimensionalization is not like when you start one and you get it. No. If you want to count non-dimensional equations, this will be like 3 and 4. You see, even as I'm doing it, okay, you have to come and remove it. That's the creativity. That's what you should be doing. And at the end of the course, that's what you should have. The score. The score you should have. So here, my del with respect to x. This depends on a small x, so we have to write the change in terms of small x. So repeat the numerator. Then the new variable is small x multiplied by the same thing, then over there. This one. So this will be this is what? R over d2 half the x. So when I multiply it, I'll get what I want. So at the end of the day, when I put them here, I will get what I want. So the squared u, the x squared. This is what? Half. That's r over d2 half times k r over d2 half. Let me bring all the constants here. R over d2, all the parameters, then the x, the u, the small x. This is K. So K. Now get my so I get my KR KR over D2. Thank you. Then the square U the S square. Now I've got it. When I put everything into equation 1, and you realize that my non-dimensional equation is different from what I gave it to you. Even I haven't prepared it. I just standing here created a new one. So here when you put there, then this becomes KR du tau equals to, this will give us what? RK. Is that okay? RK. Then 1 minus U minus beta KU times, this is R V over beta plus D1 then times 1 KR over D2 the square U the X squared. So this cancel this and this run through. Make sure that it run through. So at the end of the day, I will get du the tau equals to what? This here, U is here. U 1 minus U minus UV plus D1 over D2 the square U N square. But once we have non-dimensional, they shouldn't go on the old terms. So I will come and redefine. Let small d equals to D1 over D2. And that's how we build non-dimensionalization. Time you see old one, we redefine. So when I redefine, then my du d tau equals to U 1 minus U minus UV plus D the square U X squared. That's 1. Now I come to the second one. Is that okay? So the second one, the vein. My vein, the T, that's the vein, big vein. And big vein is now depend on small vein. So I can write my change rule. I can find on this with respect to small vein. I can find change on big vein with respect to small vein. Then times the same term, the vein. And my T is in terms of tau. So I should introduce the tau times the same term, the tau over. Come and make it T. So I'm changing the whole of this to this one. I'll find these two. So vein over small vein, you get what? That is R over beta. You okay? So the vein, big T is R over beta. Then tau the tau. Tau the tau. This one is R. Is okay? Times R the vein the tau. So I will get R squared over beta the vein the tau like this. Then you change all these ones to the new ones. Yeah. So here my this one, let's change this one. Similarly, a square with respect to big A square as well. Partial with respect to x, and big V with respect to x. Board mass, bracket first. So straight away, big with respect to this big S defined in terms of small s, so I can find the change in big S with respect to the small x. So I have to introduce small x times the same thing, small x this time over big X to bracket. So I can find the change of this with respect to this. Then partial V with respect to big V has been defined in terms of small v. I have to find change with respect to small v times the same thing, v over. Now I want to change your x, but big S is defined in terms of small x. So I have to introduce small x times small x, and this time over big X. Shakalu. So let me write my new equation somewhere because I will train it. UV plus D V small v times of small v is okay. Tau times tau t. If I want to derivate big V over that is R over beta times R v tau. Let me write it also somewhere. R squared over beta dv d tau. So here what do I get? This with respect to this, what do you get? That's R over D2 half. Partial with respect to x. Then this one, with respect to v. That will be R over beta. R over beta. Then partial v with respect to small x. Then x, small x with respect to x, R over D2. D2 all raised to the power half. So at the end of the day, you'll get this raised to the power half. So you get this R over this. Then R over beta, yeah. So you get R over D squared is under R, so R squared. So beta D squared. The square v over the x squared. That's partial squared v with respect to x squared. Yes. So now I come and put in the second equation. So putting everything in the second equation, there's a possibility that we redefine, we add one more equation to non-dimensional equation 2. So here, putting everything into equation 2, you can label them maybe 7. The first one, maybe call it 7. Here 8. So putting minus alpha then is what? Is then equals to beta over r. So r over beta small v. Yeah. Plus gamma u is what? U over k equals to small u. So this will be ku. Ku. Then big V is what? R small v over beta. Then plus d2. Then this is what? R squared over beta d2 square v with respect to x squared. So r squared. So r over beta. R over beta. R over beta. That is why we did that. R over beta. Yeah. So then we get what? R dividing the tau is minus alpha v, then plus gamma kappa uv, then plus let's cancel this. So we have what? R partial squared v over partial x squared. Why there's a square? Oh, there shouldn't be square. There shouldn't be square because half. So this should go. This should go. No, it's there. R square, yeah. Square. R square, yeah. Because from there we had r times that. So now we divide through by the r. We divide through by r. We divide through by the r. What do we get? Then the tau minus gamma over r plus alpha kappa over r u plus r over r the square v the x squared. So this is v. So it means that we have to redefine this and redefine this and add it to your non-dimensionalized equations. You get it? So any letter I can say maybe c equals alpha over r, or maybe let me use psi, and then maybe phi equals what? Alpha k over r. That will get a new equations. Or if you want me to use a and b, it doesn't matter. A, b, and add it to your non-dimensionalized equations. is du d tau equals to u1 minus u then plus del square u then x squared d. And you will get v over d tau equals to minus av plus, yes, until now the new non-dimensionalized equations, the new non-dimensionalized or the non-dimensionalized is okay equations. We have the u, the tau, you get it, u1 minus u is okay, minus u v plus d partial square u with respect to a squared star, then the v the tau is minus a v plus b u v plus the square v with respect to x squared. Like this. So here, now we can perform a lot of analysis. We can look for local solution as well as global solution. And we know methods for determining a global solution. The Lyapunov direct method, we have Poincare-Bendixson theorem, we have Dulac theorem, we have Bendixson theorem. You can use any of them. It's okay. Yeah. And to look for a local solution, that's the fixed point. And to get a fixed point, you put the u, the tau to 0, partial squared of u with respect to x squared to 0. Okay, and this one to this also to 0. So that will give us 3 fixed points. So that one is obvious. You get it? Then After getting that, we can go ahead. We can go ahead and find the. So let me give that a fixed point. So the fixed point. So to find a fixed point, these things they are elementary. Find a fixed point. Okay, put what? Du tau to 0 partial squared. Is okay. X squared u to 0. Then divin du tau to 0 squared vin small x to 0. So this will give you 3 fixed points. So the fixed points okay. U star vin star 0 0. Then we have U star vin star. That's putting them to 0. Solve them simultaneously. So okay. These ones. Yeah. You get 1 0 and U star vin star. This one. That was B 1 minus B. Now looking at this, the second point here. If B is what more than 1, what do you get? You get negative, which is impossible because population cannot be negative. And these are the things you should always be thinking. That we can apply. The math you have learned. Your first point cannot be negative. So it tells you B, and if B is also maybe negative, let's say negative 1. If B is negative 1, what do you get? 1 minus 1 is 2. It cannot be more than that. So it tells you that this one should be between 0 and 1. Do you get it? Because you have non-dimensional, so the height is 1. So this is where you have to bring your condition for all 0 b less than 1. And then after you have got your first point, you have to interpret each of the first points. Like 0 0, what does it mean? 0 0. And always 0 0 is what? It's obvious for population model. 0 0 is always the first point, one of the first points. And 0 0 tells you that we don't have what? Prey. We don't have what? The predator. For instance, Hawking here. Is okay. So 0 0 tells you that when the two of them come together, what will happen? Is okay. And once predator and prey come together, is okay. The predator will eat what? Will eat the prey. Prey population. That means that the prey population will go down and predator will go up. And that is what? Instability, unstable. Is okay. Unstable means what? More is added. More. So this tells that 0 0, you get a saddle point. 0 0 is obvious. You get a saddle point. Where for this one, the eigenvalue for this one is going to be negative. And the eigenvalue for this one is going to go positive, like this. You get a saddle. The reason why this is going to be negative is that this one, the population, that's the prey. This will be eating this one. So this one will go down. Is that okay? And this one will go up. And once there's a positive sign, it's unstable. So it tells you that when the two will come together, they will eat the prey. And that is the meaning of what the 0 0 is. Okay. So this is going to do it. And here the prey population is 1 and predator is 0. It means that the prey population is at its peak. So this means that suppose that we have a prey. Is that okay? Like maybe I take lion and zebra. We don't have a lion and we have zebras at its maximum. We have plenty. And then 0 means we don't have a lion predator. So if one comes, what will happen? If one, that is 0 here, then we don't have ideal situation. So if even one comes, what will happen? And once one comes, what will happen? They will eat this one. So it tells you that this one is also going to be unstable. This one is also going to be your unstable fixed point. You can find your eigenvalues and that. But this one, which we are in dilemma, which can be stable for a particular condition and stable for another condition. And here, look at it. That is why we are restricted b between 0 and 1. So it's a proper fraction. So it tells you that b is a proper fraction from 0 to 1. It can be 1 over 3, it can be half, it can be maybe 0.7. You get it? So this tells you that the two of them exist. We have prey there and we have a predator. And this is the rare situation. That's what most people are interested. When the two of them exist and they are not at their peak, what will happen? Will the prey go up or predator go up? Or if prey will go up, or under what condition will prey go up? And under what condition will predator also go up? Is that okay? So this is the most important fixed point among the three. But these things, I will leave it to you as these things here. On a graduate student, even a veteran can do it. These things. Find the equilibrium point, blah blah blah, is not a way. Now, once we have this one, a diffusion system, is okay. System of diffusion or reaction diffusion equation. Then we are also interested in what? In wavefront solution. Is that okay? That is, as what the predator and prey are moving from one country to another. Is that okay? What happens? That called wavefront solution. Do you get it? And here, Duba et al., they assume that the population, is okay, the two populations, they are moving with a constant speed. They are moving at a constant speed. And in most of the models of diffusion, they assume that they are moving with a constant speed. That means, for instance, if you take maybe Nigeria, it means that the people who are coming, they are from Europe. Is that okay? The person arrived today and the person arrived tomorrow. The speed of the plane to Ghana is the same. That is it. Is that okay? Constant. So wavefront solution. So once we have a diffusion, one of the terms we are interested in is wavefront or traveling wave solution. Travel wave solution. What is wavefront solution? Now look at U and V. U is a function of what? Tau and T and X. So U is a function of tau and X. V is also a function of tau and X. Tau and X. Is that okay? Yeah. So now, once I'm assuming that, then I can say that let or certain this equals to what? U depend on Z. and then V also depend on C, where the Z, and here I want to follow Dubai 1983. Is that okay? What they do? They assume that they are moving in a negative direction. So once a negative direction, then it's a positive. Because we have done what? Shifting operator. Shifting operator. Is that okay? Or Laplace, well, we did Laplace transform undergraduate shift. Is that okay? If you shift to the right, then it's negative. So if you have f of x and I want to shift it, maybe a unit to the right. Is that okay? Then once I want to shift the h unit to the right, then to be x minus what? A. If you want to shift it to the left, then what? It will minus a. So x minus a. Then this will be what? F of x a. Is that okay? That's the shifting operator. Shift. So here they what? Assume that it's moving on in the decimal. They shift it to the left. That's the negative. So that will be x plus what? With a constant speed times the time you have changed the time for tau. So where is z is this? And the z is a new distance. Why are you saying z equals x? X is what? Is a direction or spatial distance, which is distance. Is that okay? And we know that if I shift it to the left, is a negative direction. If we're to be positive direction, x minus c tau, that would be positive direction. All right. Where x here is the distance. This is the time. And how do you define the speed? Speed, c. And I gave you the notes, and nobody has ever even simplified this. Speed is what? Distance over time. And I even gave you the book. So the speed is the c, and x is the distance, tau is the time. So you make this one aside. What do you get? X equals c times tau. Have you seen it? When you send this one here, what do you get? You get what? X minus c tau equal to 0. So you equate this one to a new distance. That's moving in a positive direction. That is why when you read movie, it just shorten it for you. Because these things are elementary. When you say applied math, you are applying undergraduate. So small things. So let's go by what was Dubai 1983. It's okay, moving in a positive direction. So once I have this, then I have to change these things. It's okay. So now my u depends on z, not a tau. And the reason for making a constant speed is that so that the PD will change to an OG. That's another relevance. Is that okay? And once you have this, now you can write your change. You have to write your change. And if you write your change, this becomes a system of OD, which is very simple, calculus. And even yesterday, I sent you my live online video for undergraduate level 200 to you. Go and learn. To watch it. I've told you, go and learn change. And all what we are doing is application of a change. Calculus of several with change. That is all. If you know these things will not be a problem. When you have maybe u is a function of what? Or w is a function of u and v. And maybe maybe u is a function of t, and v is also a function of t. Then to write your change rule, this is the w. Is that okay? W depends on u and v. U, v. Is that okay? This means we are moved from w to u or v. And u depends on t. So t here, this also depends on t. Because our final destination is 1, we're going to go ordinary derivative. If our final destination is 2, then we use a partial derivative. That's the difference. And I've told you several times these things. Are they in changes? Non-dimensional is here or you change it. These things change it. If you use how to change this one to ODE using these two equations, is this. That's undergraduate, we teach you all these things. That's the basis for you to go into postgraduate. Postgraduate, you don't learn entirely new things. So this is the W, the T. I'm going to T. I can pass here to T or here, all means plus. But because W depends on what 2 here, I'll use a partial. Partial W with respect to U. This means I've jumped from W to U. Then I'm going to T. So from U to T. U depends on one verb, so I use ordinal. So the U, the T plus, or means plus. Then from W I can go to V or U. So it depends more than I use a partial. Partial W with respect to V. Then V depends on 1, so ordinal. The V or the T. That's it. Is that okay? And at the end, some of you can tell me I've searched online all the books, I can't find it. Then you should be shame unto you. You shame as yourself. These things, undergraduate, is in the books. It's very common. Any multivariate calculus book, you see it. Because you do it well, but you don't want to understand. And me too, that already, you go back, go and learn it, and come and read it. So how did you write this? Or how did you get this? Yeah. So here, we want to now, it means that our U depends on what? U depends on tau and X. U look here, we are going to Z. Is that okay? We are going to Z, but U depends on what? U depends on Z. Is that okay? And then Z depends on what? X and tau. Is that okay? Those are the new values. This is a constant speed. Is that okay? So U depends on Z, and Z is also a function of what? X and tau. Or let me write it. U is a function of Z, and Z is also a function of T and what? Tau. It means that for us to move, this is U. From U, we go to what? Z. And Z, we can go to what? X or tau, like this. So now, it turns out that we change the derivatives. Now this U will depend on X and tau to U. It will depend on Z. So this is we change them. So it turns out that because my final destination is 2, I use a partial. Is that okay? So partial U with respect to X. Partial U with respect to X will be what? From here to here is du dz ordinary. this was partial, more than one, partial, sorry. From the question, change all of them, so partial, is okay. So from U depends on 1, so use the ordinary, is okay. Then we move to X, but Z depends on 2, so use a partial. So this is partial dz with respect to X. Now look here, we want to change the U tau X depend on 2 dz. It means I want to change partial X with respect to uz. Is that okay? So the Z and X, partial Z with respect to X, equation connecting Z and X is here. So when I find partial Z with respect to X, I'll get 1. So putting it here, it tells me that my partial U with respect to X is what? Is U dz. But I want second derivative. Is that okay? So once I want the second derivative, then my second derivative, the square U with respect to X squared, the U with respect to X, the U with respect to X. So if this is this, and then the U there with respect to X will du dz. So this is d dz, then du dz, and this is what? The square U dz squared, partial U with respect to X squared. That is one into ordinary. Ordinary derivative. Then we need to also change this one. So beginning, with tau, partial U big U with respect to the T. Is that okay? Because it depends more than 1. I know one. Do my attention. Shaka rule. So here, let's find. Let me draw my diagram again. The board is too small. That's why I want to go there. U depend on Z, Z depend on X and tau. So what do we get? The U, the partial U with respect to tau. It means I'm moving from U to tau. Now from here to here is 1. So ordinary du dz times, this depends on 2, so partial Z with respect to tau. So what do we get? Partial U with respect to tau is what? Du dz times partial equation connecting Z and tau is this. So partial means this is 0. So this is 1. 1 times C is what? C. Like this. So my partial U with respect to tau is C du dz. Like this. Then you can also do for this and that, and then you write away. Means the sum of all ODs. You get it? Yeah. So try it. Then it means that the first equation, you can call the earlier one. Call it maybe 8. This is 9. Putting into what? And do for this one that. So putting equations 8 and 9 into equation star, we get C du dz equals what? U1 minus uv plus. That one we get what? The squared u over dv squared. So similarly, then the other one, we get a similar result. So we get C dv dz equals to minus av plus b uv plus the squared v over dz squared. Now it's a system of ODE. So you can look for your fixed point. Is it okay? You can look for the fixed point. Oh, there is D here. D, yeah. So you can look for a fixed point. And fixed point, I will leave it with you. You go and find a fixed point. Where is it? So here, now is the second order differential equation. You can convert to a system of first order. Is that okay? And I want to have taught you, you know how to do it. Is that okay? So yes, or let's. So now the next step is what? Convert the system of second order. Order ODEs into first order ODEs. So what is here? But look at the diffusion. They considered what? A situation where the diffusion coefficient, the ratio of what? The diffusion coefficient is 0 at first case. In a situation when it is not 0. You get it? So they did all the two. And these are the terms that you should be thinking of. You know that D is what? Ratio of D1 over D2. So if D is 0, that if D is 0, what does it mean? It doesn't mean that D1 is 0, D2 is 0. If D1 is 0, 0 is 0, is what? It's infinity. So it tells you there's 0 over D2, which is 0. It tells you D2 is arbitrary. And the D1, which is 0, that means that the prey is D0. That means what? The prey is what? Is not moving from what? One country to another, but predator are moving. It's searching for them. You get it? And these are the interpretations that, or analysis. Is it okay? Or discussion. These are the people, what the people want to hear. Once we say this is 0, understand quite well, you understand it. But if you say this is 0, mathematically, if it's 0, the numerator must be 0. And numerator, what does it represent? That's the diffusion. The movement of the plane. So when D is not 0, it tells you what? All the two are moving. You get it? So let's follow their ideas. So they assume that if d equal to 0 implies that d1 equal to 0, or in other words, if the coefficient of the prey is negligible, is small as compared to the coefficient of diffusion for predator. Suppose maybe the prey d1 over d2. This is 0.000001, and this is something like 0.9, or this is 8.2. You see that mathematically this will be very small number, negligible, approaching 0. That's what d equal to 0 means. That means that the predators. So when the diffusion coefficient is high, it means that the predators are seriously searching for the prey. They move everywhere, all over. It's okay. This is what African quality move everywhere, but the prey they move very slow. Is that okay? So here, if d is 0, then this equation becomes what? This part go to 0. You can divide by 6. So du dz is equal to what? 1 over c u1 minus u, then 1 over c u. Let me call it star 3. Then here there is no d. Then we have c div dz equals to minus a plus b u plus d squared over z squared. So you have to change the second one. Put this 0, this 0, and solve. One of the answers you get is 1, 0. When you are doing it, this 1, 0, fixed point, 1, 0. If you find a fixed point, put this to 0, this to 0, this to 0, and this to 0, 2 by 2. From last semester, every topic there we teach is there, and this is level 300. So what I'm teaching level 300. Dominic, you have to go and revise your note. If you put it to 0, look at it. U1 minus U vin equal to 0, 1. Then what? Minus A vin plus B U vin equal to what? 0. So Dominic, do you want me to teach you how to solve simultaneous equation? This, I'm afraid. Is that okay? At this level. Simultaneous, this one. Solve it. One of them is 1, 0. Find U and vin. Even if we see that if we put u equals to 1, this is 0, then is 0, this is also 0, it will satisfy. Have you seen it? I've been telling you that if I give you on a guy question, they can't do it. And that's what I've been doing. They can't. Tomorrow I will teach them level 4 at the same time. You hear that they won't ask. And I've given the note. I've simplified everything. Give me a note. Everybody has a copy. My video, every time they have it. I gave to assignment, they had it wrong. Finally, everybody has it correct. And then you go through you. Okay, let's change the second one. Moving to the first order. So to change to first order, what do we do? First order, let me use maybe even any letter, maybe R or M. So let M depend on Z be what? Vin. Is that okay? Then the M dz equals what? The Vin dz. Because the second derivative, we do have 1, n minus 1. And these things we have done in class. First and second, every day I come there. Change it. I should have write it for you straight away. These things. You will be telling me. You will tell me Dr. Bang, escape this one. So once we have this, then we have to differentiate them. Let me call here 10. Here 11. Is that okay? So let's differentiate them so that we get these things. So differentiating, it means that this depends on them. Is that okay? Differentiating equation 10 with respect to the tens in 10 with respect to z. Even one of my videos, the computer network, the diploma, the divergence are taught, I will teach them. They have learned it, but they can't recall. I've given them material, even the video I've yesterday I did. When you differentiate this, what do we get? The M, the Z. It's a different equation 10, but the M, the Z will the Vin, the Z. But the Vin, the Z, is that okay? This will give you the M, the Z, is that okay? Oh, sorry. Let the M, this be M1. We are changing to linear variables, is that okay? So this should be M2. Z. So the Vin, the Z is what? Is M2. So the M, the Z is what? M2. So this will be what? Let me call the 12 or star, 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 star. So we have got one equation in terms of first order. So this one will maintain. Then we differentiate this one and come and put it here and get the second one and add it to make it 3. Is that okay? So here, differentiating. Is that okay? Differentiating the terms in equation 11 with respect to Z. We get, what do we get? We get the M2 dz equals the squared Vin with respect to dz squared. So dz squared is here. So we make dz squared the subject here. And come and put it there. So here, making this one the subject from equation star 4. Star 4. What do we get? The squared Vin d1 dz squared equals to Hmm? C div dz plus AV minus BU. The question is answer is laughing. Last semester exams. What your differential of constant or differentiate the 10 on your 10 masters. C, then the V or the Z is what? Is M2 plus A, is that okay? Then the V is what? Is M1. M1 minus BU. Bear in mind that we did not change the U. Is that okay? So V is what? M1 like this. So at the end this is what? The second one. The second equation. Is that okay? Yeah. This is we maintain this one, this and that. So this equation star 6. So we combine 1, 2, 3. Is it okay? And then find our fixed point and then study the stability. Is it okay? So now we are converted to a system. So 1, 2, 3. 3 equations. So this is M1. M1. So here our du dz equals to 1 over cu 1 minus u over c u. Then the m1 dz equals to m2. Then the m2 dz is m2 plus a m1 minus bu m1. So these are our new set of equations. Is that okay? And now we have to find the fixed point. We have to find fixed point by putting the derivatives to zero. If I have opportunity, I'll be asking them questions. You hear. So to find the fixed point, we put what? We put du dz equal to 0, the m1 dz equal to 0, and what? The m2 dz also equal to 0. So 1 over c u 1 minus u minus 1 over c u equal to 0. Let me call it 12. One zero, 0, 1 is not a fixed point. What is the system? System of equation. Du1 is what? Partial what? U with respect to what? Tau equals what? u1 minus u plus minus u v plus partial squared u with respect to x squared. Then partial u with respect to tau equals what? Minus a v plus b what? u v plus, this is d, partial squared v, and I will find it over it. So if you put the derivative to 0, what do you get? If you put the derivative, putting the derivative to 0, derivatives, I have it to that one to 0, what do you get? You get what? u1 minus u minus uv equal to 0, equation 1. av plus buv equal to what? Equation 2. Look here. If you are claiming that u star v star equals what? 0, 1 is a fixed point, check whether it satisfies. Adai, you help me. In place of u, we are putting what? 0. Then in place of v, you will put your 1. Whether it satisfies, is okay. If it's a fixed point, u is what? 0, 1 minus what? 0. Then what? Times 1. What is what? 0. Then the next one, you should also satisfy this. What do you get? Negative a times 0 plus b1 times 1 b so minus a equal to 0. So a is what? If a is 0, then there will be no this part. Have you seen? It doesn't satisfy. If u is 1, 1 minus 1, 0. This is 1, this is 0. It satisfies. This is what? 0. This is what? 0 times this, 0. This is their problem. They want me to solve this class one way. Meanwhile, they are doing it over and over. If you want to do this, u1 minus u equals uv. Until today, dear, I won't finish. When you come to me, now look at this. Or minus u, minus uv. We can factor u out. Simple simultaneously, we can't do it. We can't do it. So this is what? U equal to 0, or what? 1 minus u minus v equal to what? So v is what? 1 minus u. You get it? So here, let me forget. Even here too, you have to find a equivalent point. The same time, you have to put the and solve simultaneous. Otherwise, if you solve simultaneous, you solve simultaneous. So here, is it my phone? Let's put it into equation 2. Is it okay? Putting u equal to 0 into what? Equation 2. What do we get? Minus av plus b times 0 times v equal to what? 0. Minus av equal to 0. What's that? we said that A should be equal to what? Gamma. What is it? Gamma 1. It was gamma 1. Gamma over something. It was alpha over something. And if A is 0, we are saying that this parameter is 0. If this parameter is 0, look at the original model. Partial U with respect to T is okay, equals to minus gamma 1. Minus gamma v plus minus alpha gamma u v plus something. Is okay. So if alpha is 0, it means that in the absence of prey, is okay. The prey, there is no one predator, which is impossible. So it tells you that A cannot be equal to 0. Is okay. 0 divided after algebra, and we pay. So I am in the winning. Go, I want to guide it. I'm multiplying two things to get 0. Either this is 0 or this is 0, or this is not equal to 0, or this is 0, or this is 0 and this is not equal to 0. But if this is 0, it will make the model work. It doesn't make sense because it means that in the absence of prey, there will be no predator, which is impossible. So it tells you that A cannot be equal to 0. So the v should be equal to 0. Restrict. And I've been telling you that once a parameter, it cannot be equal to 0. So this tells us that A should not be equal to 0. The v should be equal to 0. From the second equation. Is that okay? So now we look for what? We have got how many? 1, 2, 3. So we look for the simultaneous. So once we had this one from the second one, we put into first one. Is that okay? So the first one, if you put it there, v is 0. This is 0. Have you seen it? So if you put v equal to 0, we have from second one. Once we are solving simultaneous, you should satisfy both. So in the second equation, v is 0, so we put it here. When v is 0, this is 0. So we get what? U minus 1 minus this. And when you get this, u is 0 or u equals 1. Have you seen u equals 1? Where is it coming from? So this tells us that the point are what? So the point are v equal to 0, u equals 0, and this. So let me write it here. And v, so v1, v2 equal to 0. So putting v2 equal to 0 into equation 1. Because this is a nonlinear. For a linear equation, that's a linear doing SS. Linear, once you solve it, it will satisfy both. Is that okay? For nonlinear, you can have several. So what you have to do is, when you get it, you should put in another equation to get the corresponding values. And even after that, sometimes you have to sketch the Cartesian and then know your parent. So v equals, if I put it, I'll get u1 minus u minus u times 0 equals to 0. So u1 minus u equals to what? So u is what? 0 or 1 minus u equal to 0. So u is what? Where u equals 1. Is it not this? So how do we? I had it difficult. We over there than so we don't into me. Solving simultaneous equation. Yeah. Fortunately, on the guy you are with Dr. Bass. Go on. So if u is 1, you put v equals 0 and u equals 1. When you put v equals 0, we have u equals 1. So that's one of the points. Look here. It should satisfy both. So when you put it here, look at it. U is what? 1. So this 1. 1 minus 1 is 0. So this is 0. This is what? 1 times 0 is 0. It satisfies the first one. Then the second one, v is 0 times this is 0. Then v is 0, u is 1. So the other is 0. So it satisfies. So it's a fixed point. You get it? So one of the points is, So point u star then star is what? 1, 0. It's a fixed point. Even equivalent point, if I have told them find equivalent point, they won't know what they should do. As if Dr. Ban has never taught in class. Then now we had u equals to 1. U equals 1 in the first equation. Is okay. So you can also put it in the second equation. If you put u equals to 1, look at it. This will go minus ab plus b what? bc. Because when u is 0, we had v to be 0. When u is 0, we put what? Please, we had u equal to 0 from equation 1. Then when we put u equal to 0, we had what? V here. That's minus a v equal to 0. We had v also to be 0. So it turns out that another point is what? Another point is 0, 0. Because 0, 0, 0 times 0 is satisfied. Then now from first one we had one another point to be v equals to this. So let's put the v equals to this. What do we get? Equation 2. A is okay. 1 minus u b u 1 minus u equal to 0. So this is what? Minus a plus au plus bu. Then what? Minus bu squared equal to 0. So this one, what do we get? Minus a plus b u minus b u squared. This quadratic in u. Go and solve it. You get what? The third point. Now we'll take quadrant from one side. The baby t. Sure. So that's how we had 1, 0. Is it okay? If you say that u star then star is 0, 1. 0, this is 0, this is 0. But look at the second equation. This is 1. So this is minus a times 1 plus. Then b times 0 times 1, 0. So minus a equal to 0. And a cannot be equal to 0. Cannot be equal to 0. If a is 0, then what is a? We define a as alpha over something. It means that this parameter is 0, which is wrong. It cannot be 0. My friend, you get it? It cannot be 0. So here too, we put what? This one to 0 and find the fixed point. Is that okay? So 1 minus c u, 1 minus c, 1 over c u equal to 0. And 2 equal to 0. Then, is it my call? Then cm2 plus m1 equal to 0, 15. Computer network. we find a fixed point. Is that okay? So n2 equal to 0. Put n2 here. Then we find m1. Is that okay? The same time, fixed point. So let me give it to you. Into senior man into be equal to 0. Now, simultaneously, medium. Medium chance I'm arguing. So after getting the fixed point, is that okay? You will get something like u star m1 m2. Is that okay? 0 0 0. Is that okay? Then the second fixed point is u star m1 m2, which is what? b1 minus b0. Then the third one, m2 star 1 0 0. So here we have two boundary conditions from the initial to here, and you see from 1 to here and from here to here. Have you seen it before? From 0 to here, 0 to here, 0 to here, 0 to here, because these are the zeros. Is that okay? So those are the boundary conditions. So we find our Jacobian matrix, which is what? The first partial derivative. So go and continue. Find what? The Jacobian. So our Jacobian of what? U m1 m2. Is that okay? Because what? You can call here f1, here what? f2, here what? f3. Partial f1 with respect to what? With respect to u, partial f2 with respect to what? With respect to m1, partial f1 with respect to m2. Then senior, I'm ending. Partial f2 with respect to u, partial f2 with respect to m1, partial f2 with respect to m2, then partial f3 with respect to u, partial f3 with respect to m1, partial f3 with respect to m2, and put the fixed point each one, and you tell whether it's stable or not. That is all. And then go and do the global solution using the Lipono. Even the Moray book I gave it to you in it, page 5. Just go and review. Then is the hidden steps. Go and bring them. So goodbye. Let's end the class. Boss.